On December 1st, NASA launched an unprecedented observing campaign for ThreeI Atlast, mobilizing more than 20 spacecraft and telescopes to lock onto this interstellar visitor at the same time. The data confirmed that Atlast is a natural comet with no signs of artificial technology, yet it carries a chemical signature and dust behavior completely unlike comets in our solar system, an abnormally high CO2 ratio nickel-rich gas compared to what we usually see, and dust that first jets toward the Sun before being pushed back by radiation. These differences suggest that Atlas most likely formed in an older, harsher stellar system with a formation history very different from our Sun. Atlast's orbit has been confirmed to be safe for Earth, but when scientists trace that path backward, they cannot confidently link Atlast to any specific parent star. Atlast emerges as an ancient wanderer carrying a chemical memory of a very early chapter in the Milky Way's history. This event has triggered a global network of scientific collaboration and hints that visitors like Atlast may pass through more often than we once believed. Each fragment of matter from a distant star that sweeps through the solar system is not just a fleeting point of light, but a rare chance to touch the history of the universe, an opportunity humanity must be far better prepared for next time. And now, we continue our journey with Atlast and the announcements NASA finally released after 43 days of silence. When government operations resumed in early 2025, dozens of silent eyes in space were already fixed on a single wanderer. That wanderer, now designated ThreeI Atlast, had become the shared target of an improvised observing campaign stretching across the inner solar system. From different orbits around Earth, Mars and the Sun spacecraft streamed measurements that turned Atlast from a faint smear into a resolved evolving object. Combined views allowed Atlast to be reconstructed in 3 dimensions rather than as a flat streak drifting across a detector. One Mars orbiter captured Atlast as a ghostly sphere tens of millions of miles away, while another mission traced ultraviolet glows where frozen gases vaporized and bled hydrogen into space. Farther out, additional probes watched as Atlast shed dust revealing how grains fanned out and curved under solar radiation. Meanwhile, a space telescope circling Earth recorded a pear-shaped halo of gas and dust, a geometry that immediately set Atlast apart from familiar solar system comets. From this synchronized portrait, engineers and dynamicists estimated the size and spin rate of the solid nucleus at Atlast's core with unusual confidence. Overlapping datasets also let researchers cross-check anomalies and avoid mistaking an instrumental glitch for a genuine feature of Atlast, a safeguard that mattered as rumours spread online. By the time agencies could speak in detail, conspiracy forums had already recast Atlast as a potential engine probe or hidden threat moving through the solar system. In contrast, gas spectra from multiple observatories agreed on the presence of water vapour and carbon dioxide, aligning at last with the volatile inventory expected for icy bodies that warm near a star. At the same time, the overall brightness evolution and dust production rate placed Atlast inside known ranges for comets, rather than for rocky asteroids or engineered structures. Those convergent measurements allowed mission teams to describe Atlast as an interstellar comet with distinctive quirks, a working identity that would anchor every deeper question about where Atlast came from and what history that frozen surface might record. When officials finally spoke in detail after weeks of shutdown and silence, the central message was deliberately simple. Atlast, they said, behaved like a comet. Gas streamed from Atlast as sunlight warmed frozen material, a coma billowed around the nucleus, and a tail stretched away from the Sun as radiation pushed dust and gas outward. For scientists used to the choreography of icy bodies, that pattern placed Atlast inside a familiar family of objects, not in the catalogue of engines or alien craft trending online. Spectra from space telescopes showed water vapour and carbon dioxide emerging in ratios that matched expectations for sunlit ice. The brightness of Atlast rose and fell with distance from the Sun, as models predict for a volatile rich nucleus that wakes flares and then fades. Jets sprayed material from localized regions on the surface of Atlast, creating subtle wobbles in the trajectory that navigation teams could track with standard comet outgassing formulas. For dynamicists, that agreement quietly strengthened confidence in Atlast. Teams also listened for stranger signatures. Radio dishes searched for repeating narrow-band emissions that might hint at artificial beacons tied to Atlast. High-resolution images were inspected for straight edges, regular arrays, or reflective panels, that could betray hidden structures riding within the dusty halo of Atlast. No such patterns emerged, and no excess power source appeared beyond the energy that sunlight alone could reasonably supply to Atlast. In press briefings, mission scientists emphasized that mystery did not vanish when Atlast was called a comet. Instead, the label drew a boundary around what needed explaining. Within that boundary, researchers could ask why a comet like Atlas carried such unusual chemistry, or how an object shaped by another star ended up threading the narrow corridor through the inner solar system. Calling Atlas natural also served a quieter purpose for many observers, replacing visions of steering engines with the humbler image of a frozen shard drifting on gravity and sunlight. Yet the conclusion was never meant as a dismissal. By resolving the question of basic identity, the community opened space for deeper puzzles about what made Atlas different from every comet catalogued before a line of inquiry that would define the next stage of observation and debate. Even after the basic identity was settled, something about the way this visitor moved refused to fit inside existing models. ThreeI Atlast followed a path gravity could predict, yet the way the comet brightened shed material and shaped a tail drifted away from solar system norms. Observers noticed that the timing of activity on Atlas did not match the simple rule that closer to the Sun means steadily stronger outgassing. Instead, the comet seemed to respond in delayed, uneven pulses as if buried layers woke at different thresholds of heat. In early datasets, dust released from Atlas appeared to surge sunward before bending back rather than streaming cleanly away from the star from the outset. The halo of Atlas took on a stretched pear-like profile that clashed with the round, soft comet familiar from local comets. Size estimates for the nucleus of Atlas derived from brightness and shape also suggested a body that might be small for the amount of gas and dust being produced. Those mismatches did not overturn the cometary classification, but they demanded sharper questions about what was driving the behaviour of Atlas beneath the surface. One line of thought pointed to composition. If layers inside Atlas were stacked differently from local comets, with more volatile ices buried under tougher crusts that could explain the staggered pulses of activity. Another hypothesis proposed that Atlas could carry fractures or cavities left from an ancient stellar encounter, guiding gas into jets that do not turn on and off in the usual way. Modelers began to tune thermal simulations, testing how an object formed in a harsher or older stellar environment might react as Atlas crossed into sunlight after long ages of darkness. The anomalies tied to Atlas forced revisions to assumptions built from decades of solar system studies. A single interstellar comet now required researchers to consider how many unseen architectures nature had tried beyond the narrow sample preserved near the Sun. As more observatories joined the campaign, the focus shifted from tracking position to building a multi-wavelength portrait of Atlas. The next phase of study would turn to chemistry and light-searching spectra for clues that might show where in the galaxy Atlas first froze. Long before the public heard the name ThreeI, Atlas had already become a moving reference point threaded through navigation files on dozens of spacecraft. Each probe carried its own mission, its own timeline, yet Atlas quietly entered almost every planning meeting where trajectories and pointing schedules were reviewed. The interstellar comet moved on a path that cut across the orbits of Earth and Mars at a steep angle, a track that allowed instruments from multiple vantage points to watch at last under different lighting and phase conditions. That geometry turned Atlas into a natural experiment in perspective. From high above Mars, one orbiter recorded Atlas as a small fuzzy sphere crossing the starfield tens of millions of miles away. The view reduced Atlas to a pale blot, but the apparent motion of that blot against background stars gave precise constraints on the orbit. Another spacecraft closer to the Sun measured how sunlight scattered from dust around Atlas, filling in details about grain sizes and the thickness of the surrounding halo. Together, these angles began to carve out a three-dimensional corridor through which Atlas moved. Closer to Earth, a space telescope with sharp optical vision tracked the expansion of the coma and the first signs of a tail. Early frames showed Atlas wrapped in a slightly elongated cloud, not perfectly round and a symmetry that hinted at uneven activity across the surface. Analysts compared the brightness profile of Atlas to reference comets from the archive, noting where those curves overlapped and where Atlas diverged. The differences were subtle at first, but they repeated across multiple observing runs. Farther afield, solar observatories designed to study the corona and solar wind logged Atlas as a minor visitor along the edge of their wide-field cameras. Within those frames, Atlas appeared as a faint streak against the constant outflow from the Sun. When coronagraph data were combined with planetary orbiter images, The path of Atlast through the inner solar system could be traced with remarkable accuracy. The combined solution revealed how fast Atlast was moving and how deeply the comet would cut into the plane of the planets before climbing back out toward interstellar space. Mission teams overlaid the orbit of Atlast on maps of known asteroid families and comet reservoirs. No local source population intersected that trajectory in a plausible way, reinforcing the conclusion that Atlast approached from beyond the Sun's gravitational sphere of influence. Backward integrations of the motion of Atlast run on clusters, and supercomputers showed a path that wandered through the galactic neighbourhood, gradually distorted by encounters with passing stars and clouds of gas. By the time Atlast arrived, any single point of origin had dissolved into probability. Imaging did more than fix the track of Atlast. High-cadence sequences captured how jets on Atlast rotated in and out of view, allowing researchers to infer a spin period and the orientation of the rotation axis. Changes in the direction and width of the dust tail of Atlast when viewed from different spacecraft revealed how radiation pressure and the solar wind sculpted grains released from the surface. Those measurements suggested that Atlast shed a mixture of fine and coarse particles, a blend that required updated models to match observations at every wavelength. As more frames accumulated, an emergent picture took shape. Atlast was not simply a point with a calculated orbit, but a textured, evolving body whose behaviour depended on the interplay of sunlight rotation and buried ices. The orbital analysis anchored predictions about where Atlast would be months into the future, while the imaging campaign hinted at deeper questions about eternal structure that geometry alone could not answer. The next step would turn to infrared eyes seeking in the glow of heated ices around Atlast, the chemical fingerprints that could narrow down where in the galaxy such a comet might first have frozen. When the James Webb Space Telescope finally turned its segmented eye toward ThreeI Atlast, the plan carried both caution and quiet anticipation. Webb had been built to read the light of the first galaxies and distant exoplanets, yet now those same instruments were aimed at an interstellar comet passing briefly through the inner solar system. Infrared detectors respond to faint warmth, and for Atlast that warmth came from ices and dust, just beginning to stir under sunlight after ages in deep cold. By sampling that glow, Webb could probe layers on Atlast that no visible image could reach. The first spectra of Atlast arrived as jagged curves on screens in control rooms, brightness rising and falling with wavelength. Each bump and dip marked a chemical bond vibrating a fingerprint of the molecules streaming away from Atlast. Teams quickly identified strong signatures of water vapour, confirming that Atlast carried the same basic ingredient that powers familiar comet tails. Alongside those lines, however, Webb recorded an unexpectedly intense signal from carbon dioxide far above typical ratios measured in comets born alongside the planets. That imbalance became the starting point for new hypotheses about Atlast. If Atlast formed in a region of its parent system where carbon dioxide could condense more efficiently than water, the interior of Atlast would naturally be rich in that volatile. Another possibility was that Atlast had spent eons in an environment where more delicate ices were eroded away, leaving deeper layers that now vented carbon dioxide as Atlast warmed. Either way, Atlast pointed to a birth environment with a temperature and radiation history, unlike the outskirts of our own protoplanetary disk. Webb's instruments also revealed subtler features in the spectrum of Atlast that hinted at complex carbon-bearing compounds. These broad blended bands did not match a single identified molecule, but they resembled signatures seen in interstellar clouds, where organic chemistry flourishes. For researchers who study the raw ingredients of life, those echoes were hard to ignore because Atlast seemed to be carrying a sample of chemistry that had unfolded under another star. In that sense, Atlast served as a portable archive of reactions that might never occur under exactly the same conditions near the Sun. The precision of the infrared measurements let teams build compact models of the surface layers on Atlast. By tuning mixtures of ices and dust in simulations until synthetic spectra matched Webb's data, researchers could test different assembly histories for Atlast. Some models treated Atlast as a loosely bound rubble pile of clumps formed at various distances from its host star, each clump adding a slightly different mix of volatiles. Other models imagined Atlast as a more uniform body that had been baked unevenly by stellar flares or nearby energetic events early in its history. Across these scenarios, one conclusion kept returning. Whatever the fine details, Atlast did not sit comfortably inside patterns drawn from comets that formed beside Earth and the other planets. The infrared view marked Atlast as an outlier, not in a way that suggested machinery, but in a way that pointed to the diversity of planetary systems beyond our own. Where some observers felt let down by the absence of obvious technological signatures, others found a deeper thrill in realizing that Atlast embodied a different chapter of cosmic evolution. Those reactions spread through the broader community as data on Atlast appeared in talks and preprints. Charts comparing Atlast to well-studied comets showed the interstellar visitor, standing off to one side, a lone point in parameter space that future objects would be measured against. In that role, Atlast became more than a transient blur crossing telescope fields, turning instead into a first reference for how often similar chemistries might appear when fragments from other stars pass briefly through the solar system. For dynamicists tracing trajectories backward in time, ThreeI Atlast quickly turned from a simple visitor into a test of how far celestial memory can reach. When computers rewound the orbit of Atlast through millions of years of galactic motion, the path of the comet fanned into possibilities rather than a single line. Each simulated route for Atlast drifted as passing stars' gas clouds, and the tidal pull of the Milky Way slowly bent the course of the interstellar comet. Instead of revealing one clear birthplace, the models implied that Atlast had been wandering so long that the parent system now lay hidden in a blur of probabilities. Spectroscopic data offered a second handle on age. The high ratio of carbon dioxide to water combined with nickel-rich gas around Atlast pointed to material forged under conditions more extreme than those that shaped nearby comets. Some teams proposed that Atlast formed around a star that had already passed through intense radiation phases or episodes of heavy element enrichment before cometary ices condensed. Other researchers asked whether Atlast might be a survivor from a distant outer disk in an ancient system preserved long enough to remember a more chaotic early galaxy. The thought that Atlast could predate the Sun carried emotional weight as well as scientific appeal. If ThreeI Atlast truly condensed in a system older than the 4.5 billion year history of Earth, then the interstellar comet arrived as a kind of elder, passing briefly through a younger neighbourhood. For observers following each update, Atlast began to look less like a transient data point, and more like a messenger from a chapter of the universe no living witness could otherwise access. That shift in perception shaped how many teams chose to frame Atlast in their reports and public briefings. From the start of the analysis, chemists understood that the real strangeness of ThreeI Atlast would be written not in images but in spectra. Where pictures showed a pale halo, the spread of wavelengths coming from Atlast revealed which molecules actually filled the space around the interstellar comet. When teams plotted the relative strengths of water and carbon dioxide bands 3, Atlast refused to sit among familiar points. Local comets formed in the outskirts of the solar system clustered in one region of parameter space, with modest carbon dioxide compared to water. Atlast appeared well above that trend, as if someone had slid the marker for Atlast up a separate axis and left the solar system population behind. The ratio alone did not imply anything artificial, but the offset forced researchers to accept that Atlast condensed under environmental rules different from those that shaped nearby ice. Additional lines in the spectrum pointed to nickel-rich gas in the envelope surrounding Atlast again, out of proportion to patterns seen around typical comets. That imbalance suggested that grains carried by ThreeI Atlast had experienced a history of heating shock or chemical sorting, unlike the gentle freezing expected in a quiet outer disk. One school of thought argued that Atlast might have formed closer to a parent star and been scattered outward, trapping metals and volatiles in unusual combinations before ejection into interstellar space. Another group explored models where Atlast inherited material enriched by earlier generations of stars embedding a memory of ancient supernovae in the dust. As these possibilities multiplied, the presence of Atlast in the inner solar system began to feel less like an astronomical curiosity and more like a physical sample from a different branch of cosmic chemistry. For some, there was a quiet sense of awe in realizing that atoms now streaming from Atlast had once assembled under a sun no human eyes would ever see. That emotional undercurrent did not change the equations, but it sharpened the motivation to understand how many other chemical paths nature might have taken beyond the narrow recipe recorded in local comets. The focus now shifted from broad composition to finer structure, pushing observers to look not only at which molecules surrounded Atlast, but also at how those molecules escaped in time and space. To answer that, teams turned their attention to the dust, released by ThreeI Atlast, tracing the strange choreography of grains that seemed to break the usual rules before settling into a more familiar tail. The first close analyses of the tail surprised teams who thought they already understood how a comet should shed material. ThreeI Atlast released dust in a way that seemed to defy the textbook picture of grains simply streaming away from the sun. In standard models, small particles accelerate outward under radiation pressure, building a graceful tail that points roughly anti-solar. By contrast, early images showed dust near Atlast, briefly surging sunward before bending back as if a hidden hand had pushed against intuition. Frames taken from different spacecraft confirmed that the odd curve was not a camera artifact, but a real structure anchored to Atlast. When researchers mapped trajectories for various grain sizes, they found that larger particles near Atlast lingered longer than expected before joining the main tail. The density profile around Atlast remained asymmetric for weeks, with clumps and knots that refused to smooth out at the usual rate. Such behaviour hinted at complex topography on the surface of Atlast, or at buried vents that opened and closed in irregular cycles. One hypothesis treated ThreeI Atlast as a body wrapped in crusts of varying strength, where some regions fractured suddenly and dumped coarse dust. Another scenario imagined that Atlast carried internal caverns, focusing gas into narrow jets, launching grains along paths briefly aimed toward the sun. Numerical experiments showed that modest differences in vent geometry on Atlast could reproduce the strange sunward arcs captured in the images. Beyond the equations, many observers felt a subtle shift in how they pictured ThreeI Atlast. The interstellar comet stopped looking like a smooth, anonymous snowball and began to resemble a weathered world with scars and hidden channels. That emotional reframing made the presence of Atlast feel more intimate, as though a foreign landscape had brushed past the inner solar system. As the activity of Atlast slowly relaxed into a more conventional tail, the early unruly phase left a lasting mark on the models. Those weeks of dust behaving badly around Atlast ensured that any broader interpretation of the visitor's meaning would have to account for interior structures, as well as chemistry, setting the stage for a deeper discussion of what kind of natural sample the interstellar comet might truly represent. For many researchers, the most profound turn in the story came when ThreeI Atlast was confirmed as natural. The absence of obvious technology around ThreeI Atlast did not end the mystery, rather that confirmation sharpened the question of why this comet mattered so much. In internal briefings, mission teams described ThreeI Atlast as a free sample return mission that no agency had to launch. Instead of spending decades designing hardware to reach another star, the galaxy had delivered ThreeI Atlast straight through the inner solar system. Every spectrum image and light curve from ThreeI Atlast represented physical material assembled under a different sun, and now dissolving into data that could be studied for decades. Seen from that perspective, the value of ThreeI Atlast was not in what some had hoped to find, but in what was undeniably present. The chemistry of ThreeI Atlast belonged to a planetary system that never formed. Earth never built our telescopes and never hosted human observers. By comparing local comets to ThreeI Atlast, planetary scientists could test whether the recipe for ice's dust and metals near the sun is typical or only one of many regional dialects in galactic chemistry. That comparison cuts straight into long-standing questions about planet formation. If ThreeI Atlast carried unusually high carbon dioxide-enriched nickel and altered dust structures, then the birth environment of ThreeI Atlast forced models of disks and young stars to widen. Simulations that once assumed a narrow range of temperatures and compositions now had to accommodate conditions extreme enough to produce an object like ThreeI Atlast. Astrobiologists saw a parallel opportunity. Molecules escaping from ThreeI Atlast traced pathways of organic chemistry that unfolded under another star, providing a reference point for how often the building blocks of life might arise beyond the solar system. If similar signatures appear in future interstellar visitors, then ThreeI Atlast will stand as the first data point in a growing argument that complex carbon chemistry is common in planetary outskirts. The emotional weight of that possibility shaped how scientists spoke about ThreeI Atlast to the public. Instead of promising hidden engines or messages, they framed ThreeI Atlast as an elder shard carrying memories of an earlier chapter in the galaxy's history. That framing invited audiences to see ThreeI Atlast not as a disappointment compared to science fiction, but as a rare opportunity to touch through measurement a world that no probe will ever reach. In papers and conference talks, one theme recurred: the true importance of ThreeI Atlast lay in the way this visitor stretched the boundaries of what researchers considered normal for comets, disks, and planetary systems. By forcing models to bend without breaking, ThreeI Atlast strengthened confidence in the scientific method while exposing how limited the current local sample had been. With that foundation in place, attention could turn to the path ThreeI Atlast followed, and the clues buried in the orbit. The next questions would ask how safely ThreeI Atlast passed through the inner system, and why the original stellar home of the comet had faded beyond recovery. From the moment precise orbital solutions converged, one message was emphasized for anyone worried about risk. ThreeI Atlast would pass safely through the inner system, never coming closer than a wide buffer of tens of millions of miles from Earth. Plots showed ThreeI Atlast skimming inside the orbit of Mars and then climbing back out with the closest approach, still farther than the distance between Earth and the Sun. For agencies wary of public anxiety, that clear separation turned ThreeI Atlast from a perceived threat into a scientific target. Navigation teams refined the path of ThreeI Atlast as new measurements arrived from spacecraft and ground-based telescopes. Tiny non-gravitational forces from outgassing on ThreeI Atlast were folded into the models, tightening predictions of where the interstellar comet would be months ahead. The resulting corridor showed that ThreeI Atlast threaded the inner solar system like a needle through cloth, precise yet harmless. No scenario consistent with the data placed ThreeI Atlast on a trajectory that could intersect Earth even under pessimistic assumptions. Once the forward track of ThreeI Atlast was secure, attention turned to the past. Researchers tried to reverse the motion of ThreeI Atlast, integrating the orbit backward through the shifting gravity field of the galaxy. At first, simulations suggested that ThreeI Atlast might be traced toward a loose region of space, where several candidate stars had once drifted. As calculations extended farther in time, the path of ThreeI Atlast began to fray under the cumulative nudge of distant encounters and tidal forces. After a few tens of millions of years, the reconstructions for ThreeI Atlast no longer agreed with one another. In some runs, ThreeI Atlast brushed the outskirts of stellar associations. In others, the comet wandered through quieter regions between spiral arms. The longer the integration, the more the starting points for ThreeI Atlast separated until no single system could be claimed as a confident birthplace. The same gravitational complexity that delivered ThreeI Atlast into the solar system had erased the trail that might have pointed home. That realization changed how many scientists described ThreeI Atlast to wider audiences. Instead of a courier dispatched from a known address, ThreeI Atlast became a true drifter, a migrant from a statistically reconstructed past. There was a quiet poignancy in knowing that material on ThreeI Atlast remembered a star that calculations could no longer recover. The safe distance of ThreeI Atlast from Earth, combined with the irretrievable origin, underscored how rare such encounters might feel, even if they prove statistically common. With impact fears resolved and birthplace dissolved into probabilities, the narrative around ThreeI Atlast could shift fully toward meaning. The next question was no longer where ThreeI Atlast came from on a map, but what era and conditions ThreeI Atlast encoded in ice and dust. Those broader implications would frame ThreeI Atlast as a moving window into galactic history, a role that set the stage for examining how the visitor reshapes ideas about time and memory on a cosmic scale. From the moment the first chemical models converged, scientists realized that ThreeI Atlast was more than a visiting comet. ThreeI Atlast had become a small but real opening into events that unfolded long before the Sun and Earth took shape. Every molecule evaporating from ThreeI Atlast carried a record of temperatures, densities, and radiation fields that no observatory in the present can witness directly. In that sense, ThreeI Atlast functioned like a time capsule from an environment the Milky Way no longer offers in the same form. The unusual carbon dioxide abundance and nickel-rich gas around ThreeI Atlast suggested that the interstellar comet formed during a phase when stars and disks were being built under harsher conditions. Those signatures pushed models of early galactic evolution to consider regions where supernova debris, stellar winds, and cold dust mixed in ratios quite unlike the quiet outskirts that shaped local comets. When researchers placed ThreeI Atlast on diagrams of chemical diversity, the interstellar comet did not erase existing trends. Instead, ThreeI Atlast extended the map, hinting that the galaxy has experimented with more recipes for worlds and debris than a single planetary system can reveal. For theorists, ThreeI Atlast offered a rare calibration point for simulations that try to grow planets inside turbulent disks. By adjusting starting conditions until virtual comets match the chemistry of ThreeI Atlast teams, could test which histories of heating, mixing and migration might plausibly have produced the observed mixture of ices and metals. Astrobiologists viewed ThreeI Atlast through a slightly different lens. If complex carbon-bearing compounds are truly present around ThreeI Atlast, then the interstellar comet demonstrates that such chemistry can arise and survive in systems far removed from the Sun. That realization turned ThreeI Atlast into a quiet data point in the broader discussion of how common the raw ingredients for life might be. Rather than answering the question outright, ThreeI Atlast framed the problem as one of statistics, urging observers to imagine a future catalogue of visitors that could be compared side by side. On a more human level, the idea that ThreeI Atlast may have condensed before Earth existed altered how many people felt about the encounter. ThreeI Atlast became a moving metaphor for memory in a universe with no living witnesses to its own beginnings. The brief passage of ThreeI Atlast through the inner system underscored how fragile such windows can be. Once ThreeI Atlast faded back into interstellar space, only the measurements and models would remain to speak for that older chapter of the galaxy. In talks and public essays, scientists increasingly described ThreeI Atlast as a reminder that local observations alone cannot capture the full story of how stars and planets emerge over billions of years. ThreeI Atlast encouraged audiences to think of the Milky Way not as a static backdrop, but as an evolving environment that leaves traces in every shard of frozen rock that escapes a distant disk. As the data archive for ThreeI Atlast settled into long-term storage, attention began to turn outward again. The next logical step was to ask how often the galaxy might send similar messengers, and whether future instruments could intercept them with greater precision than ThreeI Atlast allowed. In that way, the legacy of ThreeI Atlast pointed naturally toward the future. The same measurements that turned the interstellar comet into a window on galactic history also set expectations for the next visitor, a transition that would shape how the scientific community prepared for whatever passes through the solar system after ThreeI Atlast. As the main observing window began to close, a new phase of work around ThreeI Atlast quietly opened on screens and servers. Raw files from dozens of spacecraft now fill archives with images, spectra, and timing measurements linked to Atlast. Teams in different countries are cleaning, calibrating, and cross-matching those records to build a unified timeline of how Atlast behaved. Dedicated pipelines flag outliers, remove known artifacts, and align clocks so that every subtle change in Atlast can be trusted. Even at this stage, preliminary plots show that several properties of Atlast fall well outside typical comet ranges. Graphs of gas ratios, dust speeds, and brightness evolution place Atlast on the edge of parameter spaces that once looked comfortably filled. To understand those fringes, researchers have formed working groups that cut across missions, disciplines, and national agencies, all centering on Atlast. Some groups focus on dynamics, others on chemistry, while yet others compare Atlast to earlier interstellar visitors and to simulated populations. Shared repositories now mirror the full dataset so that a modeler on one continent can test ideas about Atlast, using observations taken half a world away. For many younger scientists, contributing even a small piece to the story of Atlast feels like being present for a first draft of a new chapter in planetary science. Senior researchers describe the collaboration around Atlast as unusually open, driven by the awareness that no single team will ever see such a visitor from all angles again. Workshops and remote conferences are already scheduled to compare early interpretations, with organisers asking each group to state clearly which conclusions about Atlast are robust and which remain speculative. That culture of transparent uncertainty turns Atlast into a training ground for how to communicate frontier science under public scrutiny. As analysis deepens, early results from Atlast will move from preprints and talks into reviewed papers and long-term models of comet populations. Those models will treat Atlast not as an isolated curiosity, but as the first anchor point in projections of how often interstellar debris might cross the inner solar system. In preparation, engineers and mission planners are already asking what instruments and response strategies would be needed if the next object after Atlast arrives, brighter, nearer, or stranger. The collaborative network built for Atlast will outlive the visitor itself, providing a framework to catch and understand whatever follows. Against that backdrop, the remaining questions about Atlast are starting to sound less like a mystery about one comet and more like a rehearsal for a coming era of routine interstellar encounters. The passage of ThreeI Atlast has forced researchers to rethink how often such visitors might appear. Before Atlast, interstellar objects felt like rare accidents. After Atlast, rates in many models quietly increased. Survey simulations now treat Atlast as a calibration point, adjusting sensitivities until synthetic skies reproduce an object like Atlast. Those exercises suggest that the galaxy may send fragments like Atlast through the inner system far more frequently than earlier estimates implied. New wide-field telescopes on Earth and in space are being tuned with Atlast in mind. Search pipelines are tested against injected signals modelled on Atlast, ensuring that future scans do not miss slow, faint interstellar comets. Engineers study how quickly an alert could propagate if another Atlast appeared with a closer approach or a steeper trajectory. The goal is to turn what happened with Atlast into a repeatable playbook rather than a lucky scramble. Mission planners have begun sketching concepts for rapid response probes designed specifically for objects like Atlast. Some proposals imagine small spacecraft that could ride shared launches and wait in parking orbits until a new Atlast is found. Once a candidate appears, those probes could adjust course and meet the visitor on a flyby or even sample return path. In those designs, ThreeI Atlast serves as a reference case for brightness speed and observing geometry. For astrobiologists and planetary scientists, the prospect of a catalogue of interstellar comets following Atlast is both thrilling and daunting. If only one Atlast can stretch models of chemistry and disk physics this far, a dozen Atlast-like visitors could redraw the landscape entirely. Each additional detection would test whether the extreme ratios and dust behaviour of Atlast are typical or exceptional. In that sense, the real power of Atlast lies in how strongly the interstellar comet argues for more data. On a human level, the idea that ThreeI Atlast might be the first in a long series of messengers alters the emotional frame. The encounter with Atlast no longer feels like a singular cosmic favour, but like the opening of a new observational era. That shift leads naturally toward the final question scientists and the public now share. If the universe is willing to send more visitors like Atlast, how prepared will humanity be when the next interstellar comet crosses the sky, from the moment detection thresholds first flagged? ThreeI Atlast, a countdown had quietly begun. Observers knew that Atlast would only remain bright enough for detailed study during a narrow slice of the orbit. Every planning meeting about Atlast carried the implicit pressure that each missed observation window would never return. As the interstellar comet approached, perihelion Atlas brightened and sprouted the active structures that made the campaign worthwhile. Those same changes marked the peak of accessibility, because Atlast would soon recede, fade, and slip back into background noise. Scheduling constraints, weather and technical glitches occasionally stole chances to look at Atlast reminders that no instrument can watch forever. Instruments that did turn toward ThreeI Atlast collected more than numbers. For many teams, each exposure felt like drawing back a thin curtain on Atlast for just a heartbeat. The awareness that Atlast would never sweep past the Sun, in quite the same way again, gave routine calibrations an unusual gravity. Conversations among scientists often returned to the idea that Atlast belonged to another system, and only crossed this sky by accident. From that viewpoint, the brief alignment between Earth instruments and Atlast resembled a rare coincidence in a chaotic galaxy. The sense of contingency made the successful measurements of Atlast feel less like entitlement and more like an unexpected gift. As weeks passed, the coma of ThreeI Atlast thinned and the tail stretched into a finer, fainter line. Exposure times grew longer to keep Atlast on plots, and eventually some facilities redirected their gaze to new targets. The disengagement was practical, but for those who had followed Atlast from the first alert, stepping away carried a quiet sadness. In the end, only trajectories and archives remained to show that Atlast had ever been here. Future students will encounter ThreeI Atlast as a set of curves and citations, not as a living target on nightly schedules. For the people who watched Atlast in real time, that knowledge amplifies a final question. When the next fragment from another star appears, will humanity recognize the same fleeting chance, fast enough to meet that visitor, with the focus poured into Atlast? As the data archives close on this brief encounter, ThreeI Atlast is already shrinking back into the background sky. In star catalogues and mission logs, Atlast will soon be reduced to coordinates, magnitudes, and reference numbers. Yet for the scientists who followed every update, Atlast has carved out a place far larger than its icy core. 3. Atlast arrived during a tense moment, slipping into the inner solar system, while agencies were silent and the world was distracted. Speculation rushed in to fill that quiet, but the story that emerged from Atlast was not about hidden engines or deliberate signals. Instead, Atlast forced humanity to confront a simpler, stranger truth. The galaxy is busy. Fragments from other stars really do pass through our sky, carrying chemistry and history that our own system could never produce. Through a coordinated campaign that spanned more than 20 spacecraft and telescopes, ThreeI Atlast turned from a faint moving dot into a three-dimensional portrait of an alien comet. Atlast showed how different a world can be when it forms under another sun, in another era under harsher light. Atlast reminded us that even a purely natural object can stretch our models and our imagination to the breaking point. In that sense, ThreeI Atlast has acted as both a lesson and a rehearsal. A lesson in how fragile our assumptions are when confronted with a truly foreign sample. A rehearsal for how quickly the scientific community must move when the next Atlast appears on survey images. ThreeI Atlast will not return. Its path leads back into the dark between the stars where no current mission can follow. What remains are the measurements, the models, and a sharpened question. When the universe sends another visitor like Atlast across our sky, will we be ready to meet that fleeting opportunity with the same focus or even greater courage than we brought to this one?